what I want to start with is the Shanders River Bridge, and you have probably seen this before. This is basically one of the examples that is fully developed in our context-sensitive conceptual bridge design course for the Shanders River Bridge, which really is a 58-meter main span. So this is a simple span with two 6-meter jump spans at the ends. We are going to be considering the mid-span location to figure out the maximum flexure demands to check our girder fatigue. So really we're looking at the mid-span location in this case, and we will be looking at positive flexure as a result. So we will be looking at positive bending moment. Now in this case, we will not have any stress reversal because no matter where you put the truck, given that this is a simple span, we will only be seeing a positive bending moment, and therefore the bottom flange is always going to be in tension, and that's what we were going to be focusing on for this particular case. So moving on, here is the cross section for the Shanders River Bridge. So remember that this is a simply supported structure with a total length of 58 meters. And here is the cross section. It has 4 girders. They're spaced at 3.4 meters for a girder, center to center spacing between the two outermost girders of 10.2 meters. The total width of the bridge is 12.78 meters. I'm showing these typical barriers, one on either side, and the width of each barrier is 0.39 meters. So we are left with a total overhang of 1.29 meters on each side. Here's a typical girder, and in this case we are looking at the mid-span cross-section. So the girder has a top flange of 550 by 35 mils. The web is 2320 by 16, and the bottom flange is a bit thicker and wider. It's 650 by 40. So one thing I want to say in passing here is that the sizing and proportioning has been done previously. This is the trickiest thing to get your head around. However, as we progress in our careers, this is an essential skill to have. And what one can do is, as one becomes aware of how to do proportioning and sizing, and one develops a gut feel for these things, we can come up with these pretty quickly to start off the process. Because remember, when you analyze something, you have to have some initial sizing, and then we go and check the design for that sizing. If it doesn't work, then we have to change it. But if our sizing is quite off from the actual solution or the optimized solution, then we would end up taking a lot more iterations or doing a lot more iterations, which has time effects and also schedule implications. But if you are sort of at the beginning of your career or a few years into it, there are lots of rules of thumb and simple calculations that we can use to come up with initial sizing and proportioning. And we spend a lot of time teaching you different simplified analysis techniques, as well as some proportioning and sizing rules. And we show you how some of the tools that are available that are not very complicated, certain charts and rules of thumb, can really help you start that process. So I would recommend that you have a look at our context-sensitive conceptual bridge design courses as a series of 3 courses, but the second and the third would come in quite handy for something like this. Okay, so that really is getting us into Shanders now. And I have put some basic sketches on various slides, but what I'm going to do today is keep the screen very dynamic, because this lesson is more calculation based, and I didn't want to just pre-write things and just want to talk you through the numbers. I wanted to be working through some of the calculations live, and that's what we are going to do. So first off, we are going to look at the Shanders River Bridge based on S6-19, and that's where we are going to start. Okay, so this is our check per S6-19, CSA-S6-19, which is the Canadian Highway Bridge Design Code. We're going to first come up with the distribution factor for our FLS1 combination. Okay, so that's where we're gonna start here. And if you remember, I had shared the formula with you for FT. So remember, the MT is given by FT, or M design is given by FT times the M truck. And this M truck is really obtained from running a stick model and running the truck on it and getting your maximum demand. So basically what we do is make a stick model with, say in this case, we had 58 meters, we run it, we get the maximum demand, that's the truck, that's the global demand on the whole cross section. Then we have the distribution factor that gives us the distribution of that global demand to a given girder. So this FT was given by this formula. Today we will learn how to apply some of these formulas in a bit more detail so that things become very clear. So it has some factors or coefficients, which I'm writing down here. And this value has to be greater than or larger than 1.05 divided by n. So S is the center to center girder spacing. And then we have these constants that we have to calculate. N is the number of girders. So if our FT value that we calculate is smaller than 1.05 over n, then we have to take at least that much. We cannot go below that. So within this, we have the mu value of WE minus 3.3 over 0.6. And this is less than or equal to 1.0. This you can look at page 274 of S6-19. So in the first webinar, I had kind of gone through all of this. So now we have to calculate the clear deck width. And if I go back here, we can see the clear deck width is from this point all the way to this point. So basically from the total width, we need to subtract out the width of the two barriers to get us the clear width. And when we do that, we get 12.78 minus 0.39 times 2, and we end up with a total value of 12 meters. Then when we go to table 3.5 of the code, what we see is that when we have a clear width between 13.5 meters and 10 meters, which is the case here because we have 12 meters, our number of design lanes is 3. So here the number of lanes that the bridge is supposed to carry is 2. That's what the design is for. But when we are looking at the analysis for fatigue, the number of design lanes is 3, and that's what we have in this case. So WE is then given by WC divided by N. So this is the effective lane width given the actual design lanes that come out of table 3.5. Okay, so we get a value of 12 over 3, which is given by 4.0 meters. So each lane is 4.0 meters wide. The mu value can now be easily calculated here. And when we calculate that value, we get 1.167, which is larger than 1.0, but mu is capped at 1.0. So the mu value is 1.0 in our case. We will move forward now and really look at DT and lambda for the exterior and interior girder. So let's look at the exterior girder first. Okay, so when we do that, what we have is an n value of 3, and when we go to table 5.3, we have a formula for this. for n larger than or equal to 3. So there are formulas for n equals 1, n equals 2, and then n equals or larger than 3. And dt is basically given by 3.65 plus LE over 150, which has to be less than or equal to 4.10. Now we had talked about this effective length, and what I had described was that when we are looking at a simply supported girder or a simple span, LE is equal to the total span. So the dt value based on this formula comes out to be 4.037, which is less than 4.10. So that value holds, that's okay, and that's the value we are going to use. Okay, moving forward, when we look at the table, then lambda is given as has a value of 0 for n larger than or equal to 3. Okay, similarly, when I look at the interior girder for these two factors, I have the following situation. I have n equals 3, and my dt in that scenario is given by this formula, 4.95 minus 3.50 over square root of LE. When I plug in the values here, I get a dt of 4.49. And in this case, there is no minimum value or maximum value. Similarly, when we look at the table, the lambda value is 0.05. So we're seeing some differences between the exterior girder and interior girder for these values. Next, what we have to calculate are the two remaining factors, which are gamma C and gamma E. Okay, so again, when I look at the exterior girder, I have to go to table 5.7 for gamma E. So for the people that are working with the Canadian code, you can use these tables and this information that I'm describing, but for others also, this is a good thing to learn. So when we look at our gamma E value, we basically have a formula when n is larger than or equal to 2. Now we know that n is equal to 3 in our case, and the gamma E value is given by this slightly long formula, which has a factor dVE, which we had talked about again in the first one, and I'm going to show you how to calculate it again. But this is the formula for this particular calculation. So I'm going to write it down rather quickly here. And this thing is divided by LE squared. Okay, so we have to figure out this value of dVE. LE is already known. Once we calculate the dVE value, then we can calculate the gamma E value rather easily. Okay, so let's move forward and try to calculate the dVE value. So here is a diagram or a little figure that I've drawn. Really what this is showing is the lane width, which is 4 meters. And I've drawn that over here. Now for S6-19, we have to center the truck as if it's aligned with the center line of the lane. So the center line of the lane and the center line of the truck have to be aligned. So if the lane width that we've calculated is 4 meters, and I have my truck sitting here with a width of 1.8 meters, which is shown in the code, then this value, which is half of 1.8, is 0.9 meters. From this wheel to the edge of the deck is my dVE value. Okay, so when I look at this figure, then I can figure out the dVE value, and what I can do then is basically calculate it as follows. I have the half width of the lane, so going from there to there, I have 2 meters, and then I can add 0.39 to that to get me all the way to the edge. And I'm going to now subtract out 0.9 meters because the dVE value is from here to here. So I subtract out subtract out 0.9 from this, and as a result my DVE value comes out to be 1.49. Now I can plug in the value into that formula that I've shown, and gamma E then turns out to be 0.3936. Similarly, when I look at gamma C, I go to the code and I have to go to table 5.5. Now in this case, what the code asks me to do is figure out the ratio of SC to S. And SC is nothing but the overhang from the center line of the exterior girders. So this 1.29 is the SC value. It's going from the center line here to the edge of the deck. Okay, so if you do the numbers, you'll see that the SC over S is 0.38, or SC is equal to 0.38 times S. Now the code has a formula when SC is less than or equal to 0.5 S, and also when it is larger than that. When SC is less than or equal to 0.5 S, the gamma C value is given by 1.0. Okay, so we've calculated everything for the exterior girder at this point. We have to do is calculate the gamma C and the gamma E values for the interior girder. Again, we go to the code. We have the N value of 3, and the table I have is 5.3 that I'm going to consult, and based on that my gamma E value is 0.0. For gamma C, I have to consult table 5.4 for an interior girder, and I have to compare my effective length with some bounds. But when my effective length is larger than 50 meters, which is the case for this bridge because I have an LE of 58 meters, then I can use a certain formula. As long as my S value is between 1.2 meters and less than or equal to 3.6 meters. So S is the center to center girder spacing. In my case, S is 3.4 meters. If this is the case, then gamma C is given by this formula, 0.3 S plus 0.64, and therefore my gamma C comes out to be 1.66. Okay, so we've got these values for both the interior girder and the exterior girder. We're now ready to go and calculate the FT values for each one of them. Okay, so let's first calculate the FT value for the exterior girder, and this is given by this formula S over dt gamma C multiplied by 1 plus mu lambda plus gamma E, and this has to be larger than or equal to 1.05 divided by N. N is the number of girders, so this value is 1.05 over 4, which is given by 0.2625. So if our FT out of this formula is smaller than 0.2625, then we'll have to use 0.2625. However, when we run the numbers and we've calculated all the values, the FT for the exterior girder comes out to be 0.604, which is greater than 0.2625, and therefore this is the value we're going to be using. Similarly, when so let's just say that this is the exterior girder. When I use the values for the interior girder, my FT for the interior girder comes out to be 0.434, and that's also larger than 0.2625. So keep an eye on these values. Exterior girder is showing me a larger distribution factor. So although my global demand is the same, I'm not going to be using a different global demand. My truck demand is what it is. That tells me that the exterior girder is going to be getting more demand as compared to the interior girder. Now, because for this bridge we're designing all the girders to be the same, it is quite likely, and we'll see that in a little bit, that the exterior girder design will be critical. Once we've verified that, then we don't need to look at the interior girder. So let's keep moving here. We are now going to look at the effective flange width calculation. So when we are looking at the bending resistances and stresses in slab on girder bridges or other bridges such as boxes that have the deck which is composite with the girder, we have to basically check if a reduced cross section has to be used. So what it is the effective width of the deck is a left side overhang, a right side overhang, and then the girder flange. So that will give us the effective width. That's the composite section that we're going to use, including this much deck and the steel girder to come up with our capacity side of things. So when we look at this whole thing, we should be going to clause 5.8. This sketch is basically adapted from figure 5.6 of S6-19, but really the BS value, which is the overhang on a given side, is given by the following formula in S6-19. It's given by 1 minus LE over 15B to the power of 3. Okay, now B is basically given by half of the distance between the edges of the flanges. Okay, so that's why this is shown as 2B, and half of that is the B value. So in this case, we can see that the B value, or the 2B value, would be 3400, which is the center to center, minus half the flange width here and half the flange width here, which makes it one full flange width. And the top flange is 550, so we end up with 2B of 2850 mils. Okay, and then the B value comes out to be 1425 mils, or 1.425 meters. You can use this formula in any units as long as your units are consistent. Okay, so when I run through the numbers, my BS value basically comes out to be 8.593, but the code is very clear that this value cannot be larger than B, because physically the maximum you can have is the center to center between the girders to get you the effective width, the maximum effective width. So if this BS value is larger than B, which in this case it is by a long shot, it's much bigger than B. So BS will be equal to B, which will be equal to 1.425 meters. So that's the typical calculation, and that is applicable for the exterior girder for the right hand side. So I'm just going to say that this is the right hand side. On the left hand side, I have to check to see if I have enough of an overhang, that the overhang value is at least this much, because of the length of the bridge, I can have the B as the full value, which is the half between the girders. So remember, this effective width comes about because of some shear lag effects, which I won't go into too much detail, but as your bridge gets longer, the shear lag is basically diminished, and you can rely on the full width. But if your bridge is only 8 meters long or whatever, just picking a number, then you'll see some reduction in this value. Now on the left hand side, what we have seen here is that the left hand side is basically going to be, let me just find the slide here, the appropriate slide. So in this case, my overhang is 1.29. That's from the center line. And then this half width is 550 over 2. Okay, so based on that, we can calculate the left overhang. So let's say that we calculate the left overhang. And in this case, it's going to be 1.29 minus half the flange width. And in this case, we are left with 1.015. So when it comes to be effective, I get a value of 1.015, which is the left overhang, plus 1.425, which is the right overhang, plus 0.55, which is the width of the flange itself. Okay, so the deck width, the effective deck width, that's going to be composite, or that can be assumed to be composite for our calculations, is given by the summation of these three numbers, which adds up to 2.99 meters. Okay, so when we look at the interior girder, obviously we have the BS, which is equal to 1.425. So the left overhang and the right overhang are both available to the maximum degree, to the maximum extent, which is 1.425. So when I multiply 1.425 by 2 and add 550 mils to it, I get the full 3.4, which is the center to center between the girders. Okay, so now let's look at what's happening here. So the B effective is basically equal to 2990 mils for the exterior girder, and it is 3400 mils for the interior girder, and we have checked that. Okay, and we also have the values for these. For this example, we have assumed a nominal haunch of 60 mils, but I am going to ignore it for these calculations. But you'll see that for AASHTO I need that haunch for some calculations, so we've assumed a reasonable value for steel girders. Usually for steel girders the haunches are a little bit less as compared to concrete. So in this case I can now come up with the composite properties, and the N value, which is the modular ratio based on the Canadian code formulas, is 7.2. So this is really E steel over E deck or E concrete. Okay, once I run the numbers, I get certain values for interior and exterior girders. It's 1.7 times 10 to the 11 millimeters to the fourth. Because we're interested in the bottom flange, we're going to look at the stress at the bottom of the bottom flange. The YB value, the depth of the extreme fiber, or the distance of the extreme fiber from the composite neutral axis, is given by YB, which is 1885 mils. So this is for the interior girder. And then my SB, which is the section modulus, which is what I'm going to use for my stress calculations, is given by 9 times 10 to the 7. When I look at the exterior girder, these values are a little bit smaller because my effective width is a little bit less. And so in that case, I have, instead of 1.7, I have 1.64 times 10 to the 11 millimeters to the fourth. I have a bottom value of 1840 instead of 1885. And finally, I have a bottom modulus, section modulus of 8.94 times 10 to the 7. So you can now see that not only is the demand on the exterior girder going to be higher, its S value is also smaller. So the nominal stress that the exterior girder is going to see is going to be larger than the interior girder. So perhaps moving forward, we only need to check the exterior girder and not the interior girder, given that our design for both of them is exactly the same. Okay, so if you remember, for the Canadian code, we have to check this function, and we'll come back to this, but really this FSR is the nominal stress, which includes the live load plus impact moment on the that's generated due to the truck. So FSR is really going to be given by the M live load plus impact. The values I've shown before did not have the live load impact value in it. But remember that we should not be putting in the whole value, because that's for the entire cross section. We have to multiply it by the distribution factor, so do not forget to do that. we had calculated the distribution factor to be 0.604, and we multiply that by the dynamic load allowance times the truck. And this value, when we do that, turns out to be 92.29, and the units for that are kilonewton meters. If I want to convert it to Newton mils, I multiply it by 10 to the 6. Because my SB value is in cubic mils, and we want to come up with values in terms of newtons per millimeter squared or megapascals. That's why I've done this conversion, divided by the SB value, and what I get for my FSR is 62.35 MPas. So this is the nominal stress with the live load plus impact. But remember, we still have to deal with this side, and we have to calculate the FSR value. So let's go ahead and calculate the FSR value now. So for calculating the capital FSR value, we are assuming that this is a highway class 1, so my ADTT, as we've discussed before, is 4,000. I could use or assume 3 lanes. I'm just going to be a bit conservative and assume 2 lanes, which is the actual number of lanes on the bridge. Theoretically, you could use 3 lanes. So then ADTTF is P times ADTT, which is 0.85 times 4,000, and I get a value of 3,400. Then my ND, because this is a simply supported bridge, is 1.0. This is the number of effective cycles that this the particular detail or location will see. And then we finally have the total number of cycles, which is given by 365 times Y times ND times ADTTF. Okay, so Y is 75 years because that's the design life. We're not assuming any changes there. Once I go through these numbers, I get a total number of cycles of 93,075,000. Okay, this is a situation where we're looking at the bottom flange, and in this case what we usually have is a stiffener welded to the flanges, and therefore the stress, which is going to be this way under bending moment, is going to be normal to the welding axis. And in this case, the stiffener welded to the bottom flange gives us a fatigue category of C1. So you can look at the code, and for the bottom flange, that's the category we get. Okay, so for that, our gamma value is the same as the C category, 1440 times 10 to the 9. However, the gamma primed value is different. It's 9.92 times 10 to the 15. And also the FSRT value is different, and that's 83 MPAs. And all of this is basically coming from our table 10.4 in the code. Okay, so now we're ready to figure out our capital FSR, which is the capacity side of things. So we start with our first formula, which is gamma over NC to the power of 1 over 3. When I input this gamma and this NC and take the power to 1 over 3, I get a value for FSR of 24.92 megapascals. And you can check that. We can see that the FSRT value in this case is smaller, or the FSRT value is larger than the FSR value. FSRT value in this case is 83 MPAs. So we have to now recalculate the FSR value by using gamma primed over NC to the power of 1 over 5. And when we run this value, we get a stress of 40.32 MPAs. this value, I'm sorry, let me just correct that. Actually, no, that's fine. So this value, 40.32 MPAs, is smaller than, now we have to check our constant amplitude fatigue threshold, which is FSRT, divided by 2. That's the S6-19 code. We get a value of 41.5 MPAs. And we've been told that this is the minimum value that we can have. So the FSR value then is basically 41.5 MPAs for our design check in this case. Okay, so we're coming to the end of this check. And what we have to do is use this 0.52 CL FSR and check if it is less than or equal to the big FSR. Because we use CL625 truck, this value is 1.0. So I have 0.52 times 1.0 multiplied by the FSR value, which was my stress, the demand side of things, and this has to be less than or equal to 41.5 MPAs. And what I find then is that my inequality is 32.42 divided or less than 41.5 MPAs, which is okay, which means that my fatigue check passes for this particular location based on the S6-19 code. The D over C value is 0.78, just for reference.